malware authors don't want to be caught. This is true of pretty much every criminal. But they will engage in a number of tactics to avoid being caught, one of which is sponsorship. This primarily applies to the latter two groups, the organized crime and nation-state people. It took a long time to figure out who made Stuxnet, even though there was essentially a fairly good idea of who actually did it. It took investigative journalism from the New York Times to actually pin it down. So they will essentially do their work for hire, especially the organized crime people. Misdirection, fairly straightforward. If you have a piece of malware and you want someone to think that somebody else did it, well, then they go back to their laziness and they'll copy code from other organizations. So if you're a Russian hacker and you want to make it look like somebody from China is the actual culprit behind the software you're writing, you can do that. You can put Chinese code in there. You can put anything. Maybe you can put English code in there. The zero-day market is the interesting point that I was bringing up with the Patch Tuesday, Malware Wednesday stuff. There is actually a thriving market for zero-day vulnerabilities. And zero-day vulnerabilities are essentially vulnerabilities that exist in software. It doesn't have to be Microsoft, it can be Adobe, it can be just about anything. And those zero-day vulnerabilities now go for significant sums of money. This is another way they can actually interact with organizations without being caught. Essentially, when you buy a zero-day vulnerability, what's happening is that you are guaranteeing the complete and total access to that particular vulnerability. So if you have purchased one of these vulnerabilities, you can write an exploit for it, and then you are guaranteed that unless somebody else independently discovers this vulnerability, that you are going to be able to exploit it on your own. And usually when the zero-day market parties meet, and they usually don't meet physically, but they will essentially guarantee anonymity to each other. And these vulnerabilities typically go for $100,000 to $250,000. It's not inexpensive. And there's actually a significantly larger market now than there was even just a year ago, especially since people found out exactly how much you could get. And then obviously we've discussed advanced persistent threats. You guys already know that. But the concept there is that you're going to be inside the network and you are going to hide your presence as much as possible. And you may even essentially put up false flags so that people will find things over here and ignore what you're doing over here. And then of course, most criminals want to do what they do to get the biggest bang for their buck. This is what I talked about earlier with egress filtering. Once you're actually inside the network, it's not enough to just be there, you actually have to have a purpose. Most of the time, people will essentially be trying to get data back out of that network. It's called exfiltration, and that's the reason you want to do the egress filtering, because if you see these traffic patterns, then you can actually figure out that something's happening. And then the reason that they do that typically is for the theft itself. I discussed intellectual property earlier, but also blackmail and ransom. I guess a very large target these days is health organizations. Health organizations have personally identifiable information and then personally identifiable health information. And if you can get a hold of those records, or even just credit card numbers, for instance, you can usually extract large sums of money for the information not to be published. It's a little bit more difficult these days. I mean, that used to be more popular, at least with credit cards, but with the health information, it gets to be very interesting very quickly because the organizations involved usually have a very, very keen interest in not having that stuff published. So people will pay depending on the circumstances. When you're inside a network, the other interesting things that malware authors tend to do is they tend to actually do network profiling and actor graphing. I assume everybody here is familiar with and/or on Facebook. Essentially what Facebook does with your friends is they will create a network graph, which is based on graph theory, which is just a map, essentially. And malware authors actually do the same thing. They will actually go into computers and then they will spread as far as they can in the network. So they will not only map out the network, but they will actually map out who is on the network. So if you get into, say, an admin assistant's computer and you get into her or his email, then what you can do is figure out who that admin assistant is the admin assistant for. So let's say you get lucky on the first try and you're automatically into the admin assistant of the CEO. Well, Now you know the CEO's name, you know the CEO's email, you have access to his schedule because she or he does too. And then from there, you can spearfish the CEO himself, and you can get information on the rest of the board. Once you have information on the rest of the board, you can start to draw a graph of who is where and what they do. And malware authors will do that, and they will actually take it one step at a time. They will spearfish one person, get the information, add another node to the graph, spearfish that person, add another node to the graph, and continue the process until they have a really good idea, and in some cases, a better organizational chart than the organization itself. So it's pretty scary stuff. And then obviously they want to go as far as possible without drawing attention. That is actually more difficult these days, simply because the way of spreading is a little bit more well known. And for those organizations that are doing the appropriate network monitoring, that sort of stuff is usually a big red flag, but it can still obviously happen.
What's that a flag like?
That's just a flag I found on Google Images. Okay, so we know what malware authors are doing, essentially, and so how do we go about trying to find them? Well, the easiest way is they leave you clues, and that clue is the actual malware itself. So we want to analyze the malware to figure out what it's doing and who's doing it and what. So there's three ways you can do that. Black boxing, static analysis, and dynamic analysis. Black box is actually defined as something that takes input, runs a particular process, and gives you output. So when you do black boxing, essentially you're just running the malware to see what it does, to see what the end state is. This is not something that people use all that much. The next two are much more popular. Static analysis is essentially where I mentioned going through the code line by line, essentially reverse engineering it. You're looking at the machine code, the assembly in this case, and you're trying to figure out what it does by examining code line by line, and you have access to what's in memory, what's in the registers, that sort of thing. Obviously, it requires a fairly specific skill set because you have to understand assembly language, and to be frankly honest, these days, most people don't program in it because there are obviously higher level languages. But then, additionally, you have to understand how things work in a computer. You have to know what the stack is, you have to know what the heap is, you have to know what a register is, why it's used, what a flag is, those sorts of things. So when you do that, you're essentially also having the problem at first of trying to obfuscate something. So unpacking it, for instance, pretty much all malware these days is packed, so that's usually given that you're going to have to unpack it. So you have to figure that out, then actually do the analysis, and then create a report. Dynamic is a little easier. It combines a little bit of the first with a little bit of the second, in that you're essentially running it in a black box, but you're using some tools in that black box to actually get more information out. So this is the way I was doing it before automated malware analysis came along. Basically, you're running it in a virtual machine that's usually not connected to the network. There are times that you'll want to connect it to the network, but most of the time you don't. So you're going to start the virtual machine, you're going to run your tools, so things like red shot for capturing registry changes, filemon for capturing file changes, procmon for process changes, that sort of thing. So you run the malware after you create your first snapshot of the system as it stands, and then once the malware is done, you create a second snapshot in all of those tools, and then you're comparing the two. It can be very tedious because there can be thousands of data points. You have to go through all of those to try and figure out what the most salient information is and whether or not it's worth your time. And then additionally, there's the outside stuff where you have to have the virtual machine in an appropriate state to start with, then you have to revert the virtual machine once you're done. Each of those steps by default usually takes 5 minutes even on a solid state drive, so it can be kind of time consuming. And then obviously you have to create your report. So this is an example, I should say, of fairly common way of looking at an enterprise these days. So you have approximately 10,000 computers in your organization. That's not unreasonable. I've seen networks that have anywhere from 500,000 to 1 million computers on them. Obviously your job gets significantly more difficult with that many computers. You may have advanced persistent threats in your network already. You may even know about them. But then the problem becomes, as I mentioned earlier, there is a shortage of talent in this particular arena. And so what you'll have 5 incident responders, and that's a very fortunate company, I might add. And only one of them will be skilled in reverse engineering, and very lucky. So assuming that this particular person has 50 samples a week, which is a low number, then each sample is only going to get 1 hour. Even if you had a second person, obviously that doubles, but you have to be able to do that work very quickly, and the process itself is not a quick one. So you're constantly butting heads with the sheer volume of samples that you actually have to handle. And then what you're doing is you're looking for indicators of compromise. And indicators of compromise are those traits of a particular piece of malware that are unique to that malware that you can actually use to identify it either on other machines or in the network. So if a particular malware uses, I don't know, port 6667, can anybody name what port that is?
What was that?
6667? Might be a little before your time. IRC. It used to be a very common way of doing command and control for malware was to have it report to an IRC server, join a channel. But that would be an indicator of compromise. Files that are created by malware is an indicator of compromise. The type of network traffic it attempts to send, addresses that it attempts to resolve, those are all indicators of compromise. So that if you need to look through a network that has 500,000 machines on it, you have to know what to look for. And that's what indicators of compromise refer to.